So today is one of my favorite lectures. I debated dressing up as an athlete. This is going to be a marathon race to see if we can get through all the material today. The only way we can do this is to leave a lot of the calculus to you as exercises. What I want to do is I want to do integration without integrating. I want to do change of variables without changing the variables. All right? The way to do this is the method of normalization constants. If you have a probability distribution, it has to integrate to 1. Conversely, if I give you a function that's non-negative and it has a finite integral, there's some constant I can multiply it by to make it a probability distribution. What's wonderful about this is if I have something that looks like a probability density that we know, and we have the correct functional form, we have the correct variable dependence, but we don't know what that constant is outside, there's a unique constant that will make it a probability distribution. And the goal today is to use that to bypass a lot of integration. So when do we have a probability distribution? Well, if I start off with 1, that's a probability distribution. If I give you 2 independent random variables and I add them, and I ask what's the distribution of the sum, that's going to be a new probability distribution, and whatever I get is going to have to integrate to 1. A good example to use for today will be sums of normals, sums of squares of normals, sums of chi-squared random variables. These are going to be great things to look at. In general, integration is very hard. But we can bypass a lot of integration by looking at the correct functional form. So in some sense, this is going to be very similar to dimensional analysis. I have worked very hard, not for most of the semester, but just for a little bit to make sure today's lecture aligned perfectly with the colloquium I'm giving at 1 o'clock today on extending the Pythagorean theorem. What does the Pythagorean theorem look like on a sphere? There is a version. And the whole idea is I want you to be able to sniff out a formula. It's very easy if somebody gives you a formula to play with it. Sometimes it's not so hard to prove the formula, but in general, formulas are tough to get. Can you get some idea of what the answer should look like before you do a long, detailed calculation? If you can, that skill will serve you well. And so the colloquium talk today, and I'll put it on YouTube, is to try to get a sense of how you would feel your way to formulas. All right, so we're going to start with the gamma function. So it's defined, and we talked about this before, gamma of s is equal to the integral from 0 to infinity e to the minus x to the s minus 1 dx. And we told we could also write it as x to the s dx over x. We talked about why writing it like dx over x is good in terms of how things scale. If you integrate by parts, you are led with gamma of s plus 1 is s gamma of s. And here we need the real part of s to be greater than 0 for things to converge. You can put in s is a complex number. We're not going to really do too much with complex numbers in this class, but it's worth noting that. This is integration by parts. So if we want to look at gamma of s plus 1, I'm not going to do the whole calculation. I have e to the negative x, x to the s minus 1, s plus 1 minus 1 is just x to the s dx. So I need to choose u, I need to choose dv. Well, it seems very natural to choose dv to be e to the minus x dx, and to choose u to be x to the s. Why is this natural? If I start doing the integration by parts, du is going to become s, x to the s minus 1, v is going to be negative e to the minus x. The boundary terms will cancel. You can see when I now multiply things and I get a v du, I'm going to have an x to the s minus 1. There's the gamma of s. I've got an s over here. That's the s outside. So again, I will leave you to do the detail of the calculations, but this gives you a sense of why it's true. If you plug in integers, we get this wonderful thing of gamma of n plus 1 is n factorial, n greater than or equal to 0 is an integer. Now if you look at this, you should be immediately upset with mathematicians for defining the gamma function like this. Right? This looks like it extends the factorial function. If I'm going to extend the factorial function, let's have gamma of n be n factorial, not n minus 1 factorial. Right? Why would we do it like this? Why do we want the parameter to be s defined this way and not this way? It turns out this has better properties for other things. So frequently when you are dealing with multiple issues, you can't make everything nice at once. You have to pick and choose. You've got to be careful. Sometimes different books have different normalizations. For most things, it's better to have things shifted like this. Not surprisingly, some mathematicians did not like this. They created another function. I believe it's called g of n, well, I guess g of s, which would be gamma of s minus 1. And so what would g of n be? It would be n factorial. And so you just shift the definition of the function. Not a big deal. It's which one is better algebraically. For most things, the gamma of n is. This is extremely useful. The reason it's so useful is it allows us to get a hand on the factorial function through analysis and calculus. The factorial function is discrete. It's products of integers. This allows us to convert products of integers to this beautiful function over here, and now there are techniques we can use to approximate this. We can use this to get a really good idea of how large n factorial is. Main term plus a really small correction. The first time I taught mathematical statistics, a few months before I taught the class, I got a copy of the book because I was at another institution, and one of the problems involved a binomial coefficient, and the book said you would think now that you have the binomial coefficient you've solved the problem, but you haven't. I'm going, no, I've solved the problem. I've got the answer right here. And the book continues, you now have to calculate the binomial coefficient. What do you mean? Oh, this book was written before personal computers. And back then to do large factorials and actually estimate what the quantities were was non-trivial. For us, go Mathematica, go Wolfram Alpha, put in 2014, choose 1008. You'll get a pretty good answer very quickly. But back then, to try to estimate how big those numbers were was a little bit of work. Why is this so nice? What's nice about the gamma function here is it's initially defined only if the real part of s is greater than 0. But this formula here allows us to extend it to all values of s. So for instance, if I wanted to, I will now define gamma of minus 1/2. How do I want to do this? I'll do it this way. I'll do gamma of minus 1/2 plus 1 is going to be negative 1/2 gamma of negative 1/2. So I'm taking s to be negative 1/2. Is gamma of negative 1/2 plus 1, this is gamma of 1/2. This is well defined. I'm evaluating the gamma function where my argument is greater than 0. No problem at all. Gamma of minus 1/2, not well defined initially. But now I can define, I'm going to define gamma of minus 1/2 to be gamma of 1/2 divided by negative 1/2. And I can use this formula to define the gamma function in other places. For most of what we're doing in this class, we won't need this. But it's nice to know this is called analytic continuation. So we're continuing our function to new inputs. We have seen something like this before. When we had 1 plus r squared plus r cubed plus ... This was 1 over 1 minus r. Now if I take r equals 2, is 1 plus 2 plus 4 plus 8, is that equal to negative 1 over 1 minus 2? Yes?
It depends if you allow for that or not.
So I add up all the powers of 2. It's so far above positive infinity, it shoots past positive infinity, comes through negative infinity, makes it almost all the way back to 0. This should be a little shocking to see a statement like this. So the question is, what do we mean by equals here? What do we mean by this infinite sum? This infinite sum can't just mean adding 1 plus 2 plus 4 plus 8 plus 16, because if we do, the only thing that makes sense is to have it equal plus infinity. What we're saying is the following. Consider this function over here. When does this function on the left well behaved? This is okay if what is true? Absolute value of r is less than 1. What about this one here on the right? When is this well behaved? When r is not 1. These two functions agree when they're both defined. So in some sense, I'm thinking of a function. And if the absolute value of r is less than 1, either one of these is fine for it. They both have the same behavior. If the absolute value of r is greater than 1, as long as it doesn't equal 1, the function on the right-hand side still makes sense. And so in some sense, we can say this is going to be our interpretation of this sum. And so this function, which initially makes sense when the absolute value of r is less than 1, actually will make sense for more values. Okay? So we're not going to get too much into stuff like this. If you like stuff like this, there is a beautiful class called complex analysis that gets into great detail stuff like this. You'll get wonderful results. 1 plus 2 plus 3 plus 4 plus 5 plus 6. Anybody know what the sum of the positive integers are?
-1/12.
Excellent. Remember to email me. The sum of all the positive integers is -1/12. All right. There are ways to make sense of this. All right. The last thing I want to just quickly state, which we're not going to use too much in class today, is the cosecant identity. So the cosecant identity is a beautiful, beautiful formula. So cosecant identity. And I give several different proofs. Gamma of s, gamma of 1 minus s is pi, I think s over sine of pi s. I want to just make sure that there is an s up top. I don't think there's an s up top. I want to double check. Yeah, there's no s up top. Good. So this is a beautiful identity. You've got to be very careful when you're proving the cosecant identity. Your natural inclination is, well, let me write gamma of s as an integral. Let me write gamma of 1 minus s as an integral. And I've got a double integral. Let me play some games. What you've got to be careful about is if you're using the integral expression, s has to be greater than 0, and 1 minus s has to be greater than 0. So initially, when you prove something like this, you only prove it when s is greater than 0, 1 minus s is greater than 0, so 0 less than s less than 1 if you're restricting yourself to real values. So you would initially prove an identity like this in a range, and then somehow you would extend and continue it. This identity is extremely powerful in relating values of gamma at one place to values at another place. We've already got formulas like this. There is one particular value of s that this is ideally suited for. 1/2. Why 1/2? Yes. So when does s equal 1 minus s? At s equals 1/2. So you get gamma of 1/2 squared is pi over sine of pi halves. What's the sine of pi halves?
1.
It's 1. So, and we know gamma of 1/2 is going to be a positive number, so we get gamma of 1/2, which in some sense is -1/2 factorial, is the square root of pi. So if I tell you 4 factorial, that's the number of ways to arrange 4 objects, 24. 3 factorial, number of ways to arrange 3 objects, 3 factorial. -1/2 factorial, okay, we no longer have a nice combinatorial interpretation of what does it mean to arrange -1/2 of a person. But -1/2 factorial, there is a way to justify that and have that equal the square root of pi. Does anybody have any recollection where this semester we have seen something like square root of pi? We have seen square root of pi in one place so far this semester. Anybody remember where we've seen square root of pi? Yes? It's the normalization constant for the normal. We've seen pi as the normalization constant for the Cauchy. For the normal distribution, a square root of pi, well, technically it's the square root of 2 pi, but we're not going to get into the great debate between pi and day and tau day as to which is better. There are advocates of both pi and 2 pi. But square root of pi comes in for the normalization of the Gaussian. It turns out it's all related to the gamma function. So let's consider moments of a random variable x that's the standard normal, mean 0, variance 1. So its nth moment is the integral from -∞ to infinity x to the n 1 over square root of 2 pi e to the minus x squared over 2 dx. If you do 50% of the n, I'll do the other 50%. Anybody want to do 50% of the n?
do such a thing as 50%?
Yeah. Do you want to do the evens or the odds? Odds. If n is odd, what do you get? 0. So this equals 0 if n is odd. Why? This is an even function here. This is an odd function here. We have plenty of decay, so everything is fine. So if n is odd, it's going to just immediately integrate to 0. So the difficulty is evaluating the moments when n is even. So let's look at mu of 2m, integral from minus infinity to infinity of x to the 2m, 1 over square root of 2 pi e to the minus x squared over 2 dx. Well, the first thing you should do is whenever you see an even function, just take half the integral and double it. So this is going to be the same as 2 over square root of 2 pi, integral from 0 to infinity, x to the 2m, e to the minus x squared over 2 dx. Right? I am deliberately writing this on the same board as the gamma function. It looks a lot like a gamma function. What is a gamma function? I have e to the negative x, and then I have x to some power, and I integrate from 0 to infinity. I'm integrating from 0 to infinity. All right, I've got an e to the minus x squared over 2. So what this is telling me is we're going to need to do a change of variable. Well, the natural change of variable to do is I want x squared over 2 to be my new variable u. So let's let u equal x squared over 2. So du is going to become, the 2's cancel, and we get x dx. So now you've always got to go, oh, okay, I've got dx. I want to change dx for du, not du in terms of this. So this is the same as dx equals du divided by x. Right, if u is x squared over 2, this means x is equal to the square root of 2u. Almost surely I'm going to make an algebra mistake somewhere. So I have a 1 over square root of 2. I have a u to the minus 1/2. I have a du. And now I get mu of 2m is 2 over the square root of 2 pi. Integral u goes from 0 to infinity. X to the 2m. All right, so that becomes 2u to the m. Right? Now I've got e to the minus x squared over 2, e to the minus u. And then dx becomes u to the minus 1/2, 1 over square root of 2 du. All right, so now square root of 2 is 2, cancels with the 2. So I have 1 over square root of pi. I have a 2 to the m that comes out. I have an integral, u goes from 0 to infinity, u to the m minus 1/2. Well, instead of writing it as m minus 1/2, I'm going to write it as m plus 1/2 minus 1. Why am I going to write it as m plus 1/2 minus 1? I want to have my quantity, x to the s minus 1. So I'll write it like this. E to the minus u du. Oh, well, what's this integral equal to? What's this integral? So it's gamma of m plus 1/2. We have 2 to the m over square root of pi. Here is the formula for the mth moment of the standard normal in terms of the gamma function. If I want to get the normalization constant, that's m equals 0. And that will give me 2 to the 0 is 1. So I get gamma of 1/2 over square root of pi. Well, I've already chosen things so that it integrates to 1. So what does this have to equal? 1. This is why gamma of 1/2 is so important. If we didn't know the normalization constant right before, we would have it right now. The normalization constant is just gamma of 1/2. We need a way, oh, what a perfect alignment, right? We stop right when we get to the cosecant identity with gamma of 1/2. This is the most important value for us other than the trivial integers. If we know gamma of 1/2, we can now start getting all these moments. Why? Well, if I want the Second moment, I take m equals 1. I have gamma of 1 plus a half. Well, I use the functional equation. I use gamma of 1 plus a half is 1/2 gamma of a half. And I now reduce it to just knowing gamma of a half. And you get all these things involving square roots of pi. You can actually use this to get a beautiful infinite product for pi known as Wallace's formula. If there's time at the end of the class, which I'm not convinced there will be, I will talk a little bit more about Wallace's formula. So a lot of stuff we've seen here. So the gamma function is actually lurking in the background in everything we've been doing with the normal distribution. There are ways to elementarily get s equals 1/2. So again, if you know the cosecant formula, then you're in great shape. But it's possible to evaluate gamma of a half without knowing the whole cosecant formula. This is the elephant gun, this is the atomic bomb approach. Right? This is proving the major theorem and then specializing it to one small case. I'm perfectly happy to use elephant guns when available. Sometimes they're not. And can you actually just do the case s equals 1/2? And the answer is yes. If you're interested, it's in the notes. Okay, a lot of stuff on the gamma function. Any questions on what we've seen? All right, so this is the gamma function. I will kill all the normal stuff now because we don't need that anymore. And now what we're going to do is we're going to shift to chi-squared random variables. So we say, okay, so chi-squared random variables with new degrees of freedom. And so this is a new probability distribution. And we'll say x has the chi-squared distribution with new degrees of freedom if the density is the following. I'll write it as f sub nu to just remind myself it has new degrees of freedom. I could do chi-squared sub nu, but we'll do it like that. Of x is 2 to the negative nu halves, gamma of nu halves to the minus 1, x to the nu halves minus 1, e to the minus x halves, I believe. And I wrote it over here just so I make sure I don't forget. Good. All right. Because I'm writing it down like this, in some sense I'm giving away the punchline that here's the normalization constant. This is going to work. This will be if x greater than 0 and 0 if x is less than 0. And so I'm claiming that this is exactly what you need so that it will integrate properly. Well, if you look at what's going on here, this looks a lot like a gamma function. So if I want to calculate the normalization constant, if I want to integrate this from 0 to infinity, it looks a lot like this. What's the really annoying difference between this equation for the gamma function and this over here? What's the annoyance? So I claim there's something between these two that does not match up perfectly that should piss you off a little bit. You should be upset at mathematicians for the definitions. Come on. What bothers you? What's different between how I've got the integrand here and what I want here for the gamma function? It's not a huge deal, but there's a difference. Any thoughts?
Is it the lack of integral or the 1/2 x?
Yeah, it's the x halves over here. I want my exponent to be negative x. I've got a negative x halves. Why would I define it like that? Why not just replace x with 2x or something like that? Well, the way you do the proof is you do a change of variables. You let u equal x halves, you go through, and at the end of the day you see, oh good, I'm integrating this, I'm going to get a gamma function. Oh, that's probably why I have a gamma function down below. I have an x to the nu halves over here. That's probably why I have a nu halves here. And this 2 over here is probably coming from the change of variable. So when you finish all the stuff at the end of the day, it's going to work out. But we have to do some work, we have to do some algebra. The question is, why would anybody choose to define things forcing us to do this algebra? Well, usually there is a reason. The cosecant identity is one of the things that bothers me because whenever I hear cosine, it's 1 over sine. To me, cosecant, I'm sorry, I said it wrong, sorry. Cosecant is 1 over sine. To me, whenever I hear cosecant, I want it to be associated to cosine. If there was good notation, it would be matched that way. It's not. Why do we have this notation here with this extra factor of a half? It's for the following theorem. If x is normal mean 0 variance 1, then x squared is a chi-squared random variable with 1 degree of freedom. Okay, that's a really good reason to use this as the definition. Squaring normal random variables will occur all the time. When you're doing statistical analysis, when you're looking at errors, you frequently assume errors are normally distributed because normally distributed errors are easy to analyze. And so you will assume that the errors are normally distributed. You'll have to deal with sums of normal random variables. It turns out not only is this true, we have the following theorem. If each xi is normal 0, 1, then x1 squared plus xn squared is a chi-squared random variable with n degrees of freedom. And of course, we always assume they're independent. This is beginning to tell you why we might care about things. If we have a bunch of independent normal random variables, the sum of their squares, and when we get to the method of least squares, we will be dealing with sums of squares. More is true. If now each xi is well, let's do it this way. I'll do it this way, I guess. I'll do yi is chi-squared with nu I degrees of freedom, then y1 plus yn is chi-squared with the sums of the degrees of freedom. So if I sum, and again, independent. So if I sum a bunch of independent chi-squared random variables, I get a new chi-squared random variable where the degrees of freedom is just the sum. Okay? Now, in all of this stuff, the question is, how do we prove this? One way is to write down the densities exactly. What could we use to deal with densities of sums? What method do we have to deal with densities of sums? Convolutions. This would be an n-dimensional or an n-1 dimensional convolution. We don't want to do that much. It turns out, however, that for a lot of these problems, if we can actually just prove this theorem in the special case when n equals 2, we're done. Only need last with n equals 2. What technique do we have if we can do the last one when n equals 2 that will allow us to get everything? It's grouping. So if we can show the sum of two chi-squared random variables with nu1 and nu2 degrees of freedom is a chi-squared with nu1 plus nu2 degrees of freedom, then we get the general case. So for instance, if I go back to this theorem over here, if I now want to look at x1 squared plus x2 squared plus x3 squared plus xn squared, well, I first group these two together. By this result, this is now going to be a chi-squared random variable with 2 degrees of freedom. I now group this with the next one. A chi-squared with 2 degrees of freedom plus a chi-squared with 1 degree of freedom is a chi-squared with 3 degrees of freedom. And we just march down by grouping. So march down. So all we need to do is prove the last one in the special case when we have nu1 and nu2 completely free. So it's not enough to assume nu1 is 1 or anything like that. We have to do the general case here. But all we have to do is prove this last one, and everything else follows for this one. Now the first one, if x is normal 0, 1, then x squared is a chi-squared random variable. That's a nice one. So this is a good way to review the change of variable method. So let's say, so proof of 1. So let's let y equal x squared. X is normal 0, 1. So you can remember the change of variable formula if you want, or you can just remember the idea and rederive it every single time. For me, I just rederive it every single time. I always forget the formula. I like to just go the cumulative distribution function of my random variable y, evaluated y, this is the probability that big Y takes on a value at most little y. This is the same as the probability that x squared is at most little y. And now we've got to be a little careful. This is the probability that that negative square root of y less than or equal to x less than or equal to square root of y. Because when we say x squared is less than or equal to y, x could be a negative number. This is going to be the cumulative distribution of my function x evaluated at square root of y minus the cumulative distribution function of x evaluated at negative square root of y. And this is the cumulative distribution function of the variable y equals x squared. Well, if I know the cumulative distribution function, I know the density by just taking the derivative. So I get the density of y at y is the derivative of this. Okay, what do I have to use to calculate the derivative of this? Chain rule. The important thing to note is the cumulative distribution function of the normal is horrendous. We do not have a closed form expression for it. It's called the error function. The name should give you some idea of the difficulty of working with it, as well as the importance. It's the error function. It tells how much we're missing by. There's a nice section in the book that goes through and talks about how you would calculate, how you would deal with the error function, how you would get a series expansion for it. In fact, a series expansion that converges rapidly. We can take the derivative, and because we're taking the derivative, we never evaluate the antiderivative. We immediately take the derivative. We get fx at square root of y, and now we take the derivative of square root of y, which is going to be 1/2 y to the minus 1/2. Then over here we get minus, now at negative square root of y, and now we take the derivative of this. The derivative of minus square root of y is going to be a minus. The minus reinforces, and we'll get a 1/2 y to the minus 1/2. The 1/2 plus the 1/2 reinforce. You get fx at the square root of y, y to the minus 1/2. And so now if we just plug everything in, we get 1 over square root of 2 pi e to the negative square root of y squared, which is y over 2. Oh, look at that. See how nicely it goes with the chi-squared? And then we have a y to the minus 1/2, which I'll write as y to the 1/2 minus 1. Let's see, is that how I want to write it? Let me think for a second. I'm trying to do this as a chi-squared.
Yeah.
Yes, I want to write it like that. And that will be my density. And so you can see this is looking like a variable with nu equals 1. I just have to note that the square root of pi is equal to gamma of 1/2. And then the square root of 2 down below, that's exactly what I want. And so I get the chi-squared distribution with 1 degree of freedom when you just go through and substitute. So again, just do the algebra slowly, and you will see that if you look at x squared, if x is normal, mean 0 variance 1, x squared is chi-squared with 1 degree of freedom. Okay? It follows immediately from the change of variable formula. All right. Now the question becomes, what about these other results? What about sums of normal random variables? What about sums of chi-squared random variables? So what I want to do is I want to go through the proof of the second statement, the sums of normal. In some sense, I don't need to do this, because it's completely subsumed by the third one. But there's going to be a really nice result that we can extract from the second one, a result that's very surprising. And that's why I want to go through that. And then in the end, we will go through and we will do the last one. So we've got 15 minutes. It's going to be a little tight. I think we can make it. All right. So we want to look at sums of 2 random variables first. So we'll look at x1 squared plus x2 squared is y. Both of them are normal, mean 0, variance 1. So again, exactly as before, what is the probability, the cumulative distribution that big Y is at most little y? This is the probability big Y is less than or equal to y. All these proofs are the same. It's the probability x1 squared plus x2 squared is less than or equal to y. All right, so this is the integral over x1 squared plus x2 squared is less than or equal to y. Now I have to have the density. The first one, it's 1 over square root of 2 pi e to the negative x1 squared over 2. The second one is 1 over square root of 2 pi e to the negative x2 squared over 2 dx1 dx2. So this is my density, and this integral is going to be the probability that the sum of the squares is at most square root of y. What object is this? It's a circle. Whenever you're doing a double integral involving a circle, you should immediately be thinking polar coordinates. So if we switch to polar, what's going to happen? The radius is the square root of y. Theta goes from 0 to 2 pi. 1 over root 2 pi, 1 over root 2 pi becomes 1 over 2 pi. We have e to the negative x1 squared plus x2 squared becomes e to the negative r squared over 2. dx1 dx2 in polar coordinates becomes r dr d theta. A better way of viewing this is it's dr times r d theta. We'll talk in a moment as to why that's a better way of doing it for higher dimensions. But now when we do this integral, the theta integral is going to be no problem. The theta integral is going to give 2 pi, which will cancel with this. And then we have the integral r goes from 0 to square root of y, e to the negative r squared over 2 r dr. Okay. And so now what do we get? The theta integral is going to give me a 2 pi, and it's going to cancel with the 2 pi over there. And so now, this is going to give me, now when I integrate, I get e to the negative r squared over 2, and the bounds of integration change, 0 and square root of y. And so we get 1 minus e to the negative y over 2. So hopefully I haven't made too many mistakes. That's going to be the cumulative distribution function of y taking on a value of at most y. So if I want to find the density, I would take the derivative of this. And so I'm worrying that I've actually lost a factor of a half somewhere. Which is not good because we do not have time to find a factor of a half. So we get fy of y is 1 minus e to the minus y halves. Oh, no. Everything is fine. Good. Everything is fine. No mistakes. Good. So fy of y, when we take the derivative, the minus signs reinforce. We get a 1/2 e to the minus y over 2. And this is going to be chi squared with 2 degrees of freedom. And if you go back to the formula and we plug in nu equals 2, well, gamma of 1 is 1. 2 to the negative 2 over 2 is a 1/2. I'm sorry, is a 2 to the, oh, did I drop a 2? No, good. It's a 1 over 2, perfect, which is what I have. I have my quantity here to the 2 over 2 minus 1, that's to the 0th power. Everything works out perfectly. This is a chi-squared random variable with 2 degrees of freedom. So in the special case that we are summing the squares of 2 normal random variables, we get a chi-squared with 2 degrees of freedom. The key was the change of variable formula to convert this to polar. Why is this the right way to do things? Well, you've hopefully taken a calculus class. R d theta, why do I want to write it like this? Theta is unitless. Think of r as in meters. So dx1, dx2, this is in meters squared. I want meters squared. If I want meters squared, I've got to have 2 lengths. R times an angle is going to be a length. All right. So this handles the sum of 2 squares of normals. And the key thing was to do the change of variable with polar. How many of you remember the change of variable in spherical? I have to really think because the physicists and the mathematicians have different notation as to what's theta and what's phi. How many of you know the change of variable for the hypersphere in 4 dimensions? Or the general n-sphere? That's what we want if we want to do the general case. What I'm going to show you is how to bypass the n-dimensional spherical coordinates. And we're going to get a really nice result in bypassing. So we come back, and all that we change is now plus dot 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 plus xn equals y, and now it's all a normal one. Okay. So we want to handle the general case. And so again, all the algebra is in the book, so if you want to just enjoy or try to enjoy, please go for it. We want the cumulative distribution function of being y. This is the probability that big Y is at most y. This is the probability x1 squared plus xn squared is less than or equal to y. This is the integral x1 squared plus xn squared. 1 over square root of 2 pi to the n e to the negative x1 squared plus xn squared over 2 dx1 dx2 dxn. All right. This is at least screaming spherical coordinates. The integrand only depends on the distance from the origin. The problem is, if you're going to use the change of variable formula, it seems like you need to know the change of variables. This is almost by name. There is some complicated relation. We have xi is some function hi of r, and then n minus 1 angles. And if we're going to do the change of variable, we're going to have to calculate the Jacobian. And we're going to have to calculate the bounds of integration. I claim the following. dx1 through dxn, the volume element, has to be of the form r to the n minus 1, and I'll just call it some hellish function c1, c of theta 1 through theta n minus 1. And then it'll be dr d theta 1 d theta n minus 1. And the reason is, I have, if I'm thinking of things in meters, this is meters to the n. So I've already got a meters from the dr. These are all unitless, so it's got to depend on r to the n minus 1. This is using some kind of homogeneity of space. And then there's just some god-awful nightmare in here. Okay? So now we need to do the integration. So now we integrate, r goes from 0 to square root of y, some kind of theta region. No idea what the hell that is. Okay? I've got e to the minus r squared over 2, r to the n minus 1, c theta 1, theta n minus 1, d theta 1, d theta n minus 1, dr. Well, when I do the theta integration, I'm going to just get some number. I don't know what it is, it's some number. And so what we get is we get some number, and I'll put a subscript n to remind us that this is coming from an n-dimensional problem. All right, we lost the camera. There we go. So it's coming from some n-dimensional sums of squares. And now we're left with integrating r goes from 0 to square root of y, e to the negative r squared over 2, r to the n minus 1 dr. What does this look like? Not exactly, but what is this close to? It's close to a gamma. Almost a gamma value. So you would do a change of variables. U equals r squared over 2. You would argue as before, do algebra. All right? You don't want to see the algebra. This is enough to give you a sense that it's going to work out. There's going to be a gamma function that's going to come out here. We could actually do this. And when you're done, when all the dust settles, we're going to be evaluating things at square root of y. We're going to get a chi-squared distribution that will come out. And because we will see it's a chi-squared distribution, so that when the dust settles, it'll be, Cn. I'll put a tilde because maybe things have changed a little bit. We'll have this is big Fy of y. We'll then take derivatives. We get f of y of y. The density will be some function over here. We'll then get a y to the n halves minus 1 e to the negative y halves. So when the dust settles after all the algebra, this is what you get. Again, it's just doing the integration, just doing the values. It makes sense because I've got an e to the minus r squared. When I put in square root of y, I'll get an e to the y, e to the minus y. This looks like a chi-squared distribution with n degrees of freedom. So whatever this constant is, it has to be whatever is needed to make things normalize. And that allows us to figure out what this constant was over here. It may change a little bit because I've taken a derivative, but not a big deal. All right? So I don't want to go through all the algebra. I want to just step back and say what was so important about this. The importance was that we had an integrand which did not depend on the angles. It only depended on the radial distance. So when we looked at the Jacobian, we had this nasty piece here. There's a geometric interpretation to what we just did. This is the surface area of the n-dimensional sphere. The function is constant on those slices. You can actually use this to extrapolate and get the formula of the n-dimensional, the surface area of the n-dimensional sphere. As a nice exercise, go through, I tabulated a little bit in the book, what's the volume, what's the surface area. Okay, so again, absolutely amazing. You can get the surface area of the sphere. If you know the surface area of the sphere, you can actually get the volume as well. If you've never seen this before, this is really nice. Volume, area. So, and over here we'll have dimension. So in 2 dimensions, what's the volume will be pi r squared. And what's the area? I'll say hypervolume if you want hyper area. So this is the area, what's the perimeter? In 3 dimensions, it's 4/3 pi r cubed. What's the surface area? Surface area of a sphere? Four pi r squared. It's not a coincidence that these are derivatives of those. If you imagine, you have a sphere and you extend it just a little bit. If you want to try to calculate what the volume will be, or if you want to calculate the surface area, if you shrink it just a little bit, you can get all of this stuff by looking at these formulas. All right, so what we have left now is we have about a minute left for the last little bit, is we now need to look at the sum of 2 chi-squared random variables. And so now, let's say xi is chi-squared nu I. So the density of nu1 plus nu2 at some point x would be the integral from minus infinity to infinity, the density of the first one at t, the density of the second one at x minus t dt. Well, because these are chi-squared random variables, this is going to have 0 density unless t is positive. So I can restrict the integral from 0 to infinity, f nu 2 of x minus t dt. But now looking at this one, this is going to be 0 if t is greater than x. So I can now restrict this to being at most x. So I now have the integral from 0 to x. The first one is going to be, I'll call its normalization constant c1. And then I've got t to the nu 1 over 2 minus 1, e to the minus x halves. The second one has its normalization constant. And then we'll have x minus t to the nu 2 over 2 minus 1, e to the negative x minus t over 2 dt. So I'm just plugging in the densities of the chi-squareds. I can pull out the normalization constants c nu 1, c nu 2. I have e to the negative x halves. I'm sorry, this should be e to the t halves, sorry. And then over here I have a plus e to the t halves. Those cancel. I pull out an e to the negative x over 2. And I'm left with an integral from 0 to x of t to the nu 1 over 2 minus 1, x minus t to the nu 2 over 2 minus 1 dt. It looks like this is going to be a hellish integral to do. And so in the last 20 seconds, Not enough time to erase cleanly. Oh well. All right. So what we now do is we change variables. Let's let t equal x times u. dt is going to be x du. And now we get c nu 1, c nu 2, e to the negative x halves, integral. Well, t used to go all the way up to x. If t goes up to x, how high does u go up to? Better be fast, guys. 1. And now we have t to the new 1 over 2. That becomes x to the new 1 over 2 minus 1, u to the new 1 over 2 minus 1. And then the other one is we can pull out an x from the other one, because now the t is going to become x times u. So we have a x nu 2 over 2 minus 1. And now we'll have a 1 minus u to the new 2 over 2 minus 1. And then dt becomes x du. So again, c nu 1, c nu 2, e to the negative x halves, x to the new 1 over 2 plus nu 2. The minus 1, I have a 1 over here, so it becomes just a minus 1. I'm left with integrating from 0 to 1, u to the new 1 over 2 minus 1, 1 minus u to the new 2 over 2 minus 1 du. Does not matter what that is. It's some constant. So I'm left with some new constant. Oh, well, I don't need the chalk. C nu 1, C nu 2, and here is the density of the chi-squared. X to the new 1 plus nu 2 over 2 minus 1, e to the negative x halves. That has to be the correct normalization constant. All right, there we go. We finished a little bit over. I am sorry. But, okay. Oh, there we go. We even lost the camera. All right.